Welcome to another Astro seminar and another presentation in the ASA ECR Symposia that are coming from all over the country, actually. So today we have Jahang all the way from Macquarie, and he's going to be giving us a talk about some of the research you did in your master's, correct? Yes. So whenever you're ready, take it away.
Well, thanks, Sven, and thank you everyone for being here. As you said, I'm a master's student from Macquarie University. So this talk is going to revolve around the research that I did during my Master of Research course. And the title is basically the title of my thesis, a new approach to characterizing radio-detected galaxies. And these galaxies come from the evolutionary map of the universe survey done using the ASCAP telescope. All right, so the talk is going to be two-part. The first part is about an agent diagnostic tool, which I developed using an SED fitting technique. The second part, it's about measuring radio luminosity functions using a statistical approach, or like a simple way of measuring luminosity functions in the absence of redshifts. All right. So I'll talk a lot about active galactic nuclei in this talk. So I want to give a brief overview of what they are. So AGN, or active galactic nuclei, they are accreting supermassive black holes in the centers of galaxies. So accretion is one of the most efficient energy conversion mechanism from gravitational mass to electromagnetic radiation. And because of that, the features of the AGN will be evident across the entire electromagnetic spectrum. And as a consequence, we have probes spanning the entire electromagnetic spectrum, like in radio, infrared, X-ray, and even using optical spectroscopy to detect the presence of AGN if we have a sample of galaxies. For instance, if you look at the optical spectra, the broad Balmer lines or strong optical emission lines signify the presence of optical AGN. If you look at mid-infrared spectral energy distribution of galaxies, in this plot here we have two colored lines, a purple one and a yellow one. There is a significant difference between the features of these two lines. The yellow line show strong emission line features. This comes from a specific class of molecules called polycyclic aromatic hydrocarbons. So what happens in a star-forming galaxy is that if a PIH molecule is in the galaxy and the electromagnetic radiation coming from the star formation processes ionizes this molecule, and by the recombination process and everything, it results in an emission line. In the case of an AGN, the radiation coming from it is so strong that the molecule itself gets destroyed. So there won't be anything left to show up in the emission lines in the AGN SED. That is the purple line here. Also, there is a significant difference in the spectral slope of these two populations, star-forming and AGN. You can see if you take a look at it from the inset here. I'm not sure if that's clear, but still. So these are all signifying features of star-forming and AGN population in the mid-infrared SED. If you go to radio, this is an image of a radio galaxy. The features like jets and lobes, if you see them, it is pretty sure that these are radio AGN. So these are some example features of how can we distinguish from AGN and star-forming population from different parts of the spectrum. So even though these features might be evident everywhere in the spectrum, there is a specific class of radio AGN called low excitation radio galaxies. They do not show up anywhere in the spectrum except in radio. But that means that if you want to see them, we have to look into radio part of the spectrum, or radio images at least. If that is the case, in order to have a complete understanding of the AGN population and hence in total galaxy evolution, we have to consider these lurk population of studies. So just by looking at one part of the spectrum and saying, yeah, this galaxy is an AGN, this galaxy is not, that approach won't work. So we have to actually look everywhere or consider all parts of the spectrum together to get an idea of whether a galaxy is AGN or not. Okay, so I talked a bit about spectral energy distribution. So simply put, SEDs are the blueprints of galaxies. So it kind of breaks down all different physical processes going on in the galaxy. For instance, the black solid line here corresponds to the SED of an AGN. It shows different processes here. For instance, the blue line here, it shows the characteristic feature called big blue bump shown by AGN. And the red line here is the infrared emission coming from the dusty torus surrounding the black hole, the galaxy. Okay, that's just an overview. So my idea here is to fit the galaxy SEDs and develop an agent diagnostic. So there are a bunch of SED fitting tools available in the literature. I use this tool called Prospect for two main reasons. One, once the SEDs fit from ultraviolet to infrared, it can extend that SED until the radio regime, even without radio data being present there. And the second thing is that in the DEST models that the code takes in to model what sort of emission is coming in the infrared, it considers two kind of clouds, both cloud and IS, interstellar medium screen. So what happens in a star-forming galaxy is that for a young star or a young massive star, that star will still be residing in the birth cloud. So the light coming from that star will be attenuated by both this birth cloud and the ISM screen all over the galaxy. For an old star population in general, they would have already moved out of this birth cloud. So attenuation will only be done by the ISM screen. So different sorts of these processes go on in modeling the SEDs, and I'm not going to the detail of what all different models are used here, but we can talk about that later if anyone is interested. So that's the code of the tool that I'm going to use. And SED fitting requires multivariate data. The more number of photometric points we have, better will be the results of SED fitting. So we need a panchromatic data set. For that, I looked at the G23 field from the Galaxy and Mass Assembly Gamma survey. G23 is the southernmost field of gamma. For other fields lie along the equatorial plane, still below on the southern hemisphere. So the gamma survey provides spectroscopic data and photometry coming from large number of surveys like GALAX for ultraviolet, VST and VISTA for visible and near infrared, WISE, wide field infrared survey explorer for mid infrared, and Herschel for far infrared. We have the panchromatic data set in terms of photometry. And this field is also observed using by the EMU survey, by the early science observations. So that catalog gives the integrated radio flux density, so the entire radio emission from the host galaxy, or if any jets or lobes are there. So that integrated flux density at 888 megahertz. And I also took the mid-infrared magnitudes coming from WISE survey, the all-WISE catalog. So a bunch of cross-matching procedures have been done, and as a final sample, I chose emission line galaxies. So only those with spectroscopic data, and also the radio flux density values. So in the end, I have 2956 radio galaxies with all of these properties set to fit the SED. So this is how the SED looks like. The red data points here are the input photometry from gamma. The blue data point here is the input photometry from EMU. This data point is not included in the fitting. That's why it's lying a bit above of the SED. And the black one here, black data point, is the radio extension done by Prospect. So there are a bunch of colored lines here. So these are different contributions coming from different processes. For instance, the blue line here is the red line here is the unattenuated stellar light. So if there is no dust in the galaxy and stars are emitting something, if you pick that up using these models, that will be shown by the red line. And if you introduce dust will attenuate this light, and that resulting emission will constitute in this blue dash line. And this difference, the attenuation done by dust, that is re-emitted in the infrared, that is shown by the brown dot dash line. I haven't included AGN as a model here. SED fitting tools has that capability to include AGN in modeling the SEDs. But for my purpose, I fit the SED only using star-forming models, and a radio flux is predicted here. So this predicted radio flux only includes the contribution from star formation. Yeah, I'll let that sink in. Only star-forming models here. And the blue data point from the EMU is the observed data. So that might include the contributions from both star-forming and AGN processes. So if there is a notable difference between the observed, the blue one, and the predicted, the black one, if there's a difference, and so that difference in energy should come from some astrophysical processes. If you have already accounted for the star formation, the remaining process in a galaxy that can contribute in a energy fashion is only most likely black hole accretion process. So we use that concept and say that if in a galaxy we see such an excess as we see here, that galaxy might be hosting a radioagent. Using that logic, we defined a radioagent selection criteria. So if the observed radio flux, the blue data point we had in the previous plot, over the predicted radio flux, the black one, if that is greater than 3, then such galaxies might be hosting a radioagent. So that criterion is shown here in solid black line. And every galaxy above this line shown here as blue triangles, those are the radioagent. That's the first part of this SED fitting. We have defined an agent diagnostic tool for radioagent. Okay, but in the next part, I want to compare this technique that I developed with a bunch of other SED fitting tools. For instance, those coming from optical and infrared. So I designed a suite of traditional diagnostic tools like PPT diagram, which is using spectral line ratios for galaxies, and another optical diagnostic, the mass excitation diagnostic diagram, and white scalar magnetodiagram. I'm not sure how many of you are familiar with the diagnostic tools, but I'm not going to the very detail of how the tools does it, but I'm happy to chat about it later if anyone is interested. So the blue data points here are the AGN, but they have nothing to do with the blue data point I showed earlier. Those are really separate. So these are the AGNs classified exclusively by these diagnostic tools. And the optical ones, the BPT and the MEX, classifies galaxies into an additional class of composites. To be as complete as possible, I include these composites among AGN in my work. You'll see why later. So we now have 4 diagnostic tools, and every diagnostic tool classifies galaxies into either star-forming or AGN. And we aim to compare all of these together. So to make the comparison seamless, I kind of defined a binary classification scheme, basically in a binary numbers from 0 to 16. In the scheme, 0 corresponds to star forming and 1 corresponds to AGN, and they are arranged in this order: BPT, WISE, prospect, and MEX. So if you look at this number, 0010, that is a galaxy classified as a star forming by BPT, WISE, and MEX. It is classified as an AGN by prospect. This might be a bit too much to take in. That's the whole point of showing this, because if you look at this diagram, it is very busy. That's only with 4 diagnostics. If you are to include an additional diagnostics from X-ray, we'll have another 6 or 8 classes piling up in this diagram, and it will be too much for anyone to comprehend. For that reason, I'm not going to talk much about this diagram anymore. Instead, I go directly to the statistics of what we found. So in the end of the comparison, if we look at the AGN identified only by prospect, that is, it is identified star forming by every other diagnostic tool. If you look at that in the entire sample of around 3,000 galaxies, you can see that 6% of the AGN in the entire sample is identified by prospect. So if in terms of the completeness of AGN's population that we have, this is a pretty nice deal, because without this an SED-based AGN diagnostic, you won't be having a complete population of AGN to perform our studies. And if we are looking at a low mass AGN, when I say low mass AGN, that means galaxies with a stellar mass less than 10% solar masses. In that subset, the prospect alone AGN constitutes around 40% of the AGN host galaxies. So this is again a very nice result, I guess, because AGN is mostly associated with massive radio galaxies. So the fact that we're able to detect low mass AGN host galaxies, again, I think, at least to me, is pretty nice. And that was the comparison. So if it is not obvious by now, I introduced a class of AGN called low excitation radio galaxies. And just to remind you, it's a radio AGN, just not present in any other part of the spectrum. So it can only be picked up in the radio image or radio methods. So, and the prospect AGN, for instance, they are not picked up by any other part of any other diagnostic tools, only by the radio selection. So that means this prospect AGN, they are most likely to be these lurks. So just to verify if that is actually the case, I used this diagnostic diagram, which is developed by Best et al. In 2005. So the diagram shows the DN4000, which is a proxy for age of the galaxy as a function of galaxy radioluminosity per stellar mass. And this selection line here, any galaxy which occupies the region of this diagram below that selection line is identified, they are identified to be lobes. And if you look at the blue data points, which are the prospect along AGN, it beautifully resides in that part of the diagram, which kind of reinforces the fact that the agent that we identified, they are with high confidence. I haven't quantified any numbers here, but still they're most likely to be loads. So just to look at the physical properties of the host galaxies of lurks, we can see that the stellar mass of these host galaxies are less than 10 to the 10 solar masses, and they're also hosted by low mass radio galaxies. Radio galaxies with low radioluminosities. And the threshold is 10 to the 23 watts per hertz. As in the case of lurks, most of the samples that I've come across with, they are either massive or they exhibit very high radioluminosity. In that sense, the fact that we are getting these lurk population with low radioluminosities, it's pretty cool. Okay, so that was the first part of the talk. It demonstrated that prospect as an acidity tool can be used as an agent diagnostic. And it selects the lurk population. And one of the key takeaways should be, if you want to identify an AGN host galaxy, rather than looking at one part of the spectrum, we should be looking at probably everywhere all at once to maximize the AGN population that we have. Another thing to look at is a quantity called AGN fraction. I haven't introduced a quantity here, but it's more like, rather than classifying galaxies into a binary scheme, say AGN and star forming, we should look at what fraction of the light coming from the galaxy is contributed to by the AGN. For instance, if the total light, let's say 40% is AGN or 60% is AGN, if you have to quantify things like that, in deriving quantities like luminosity functions and getting a measure of what is the light contributed to by the AGN in the universe, it might be a better measure. That was the first part. I'm not sure how you all take it. It's a bit heavy, I know. It's my entire thesis, but I did it for 1 year. That's why I understand how it feels, but I have to do it. So, luminosity functions. So, are you familiar with luminosity functions? Okay, good. That makes my job easier. So, this figure has nothing to do with luminosity functions. I just like it. Sorry, that's why I put it here. Simply put, we all know it's just the number density of galaxies in the per luminosity bin. So it basically gives us a distribution of galaxies as we go up to different redshifts. And it is estimated through a technique called, a method called 1 by V max technique. And this, if you do all the stuff dictated by this equation and you plot the luminosity function, this is how it will look like. This is the radioluminosity function derived by Tom Moch and Ilan Sadler in 2007. And they analyze the luminosity function separately for star forming and AGN population. So this is going to be my reference for entire part of this second part. I will be deriving luminosity function, radioluminosity functions. I will also divide my galaxies into star forming and AGN and perform the analysis separately. So completeness is one thing that we should not forget when we talk about luminosity functions, because every observational sample is constrained by the flux limit of the survey that we're looking at. So this diagram shows the completeness of the EMU sample that I'm dealing with, the radio sample. So until around flux density of 2 millijansky, it's fine, it's all nice and good. But if you go to flux density values below that, the completeness of the sample starts declining rapidly. But if you're using the entire sample here, the 1 by V max technique that I mentioned, it takes care of the completeness thing. There are ways to do it. So if that's done, this is not a worry. But since we are dealing with luminosities here, especially for radio galaxies, we won't have optical counterparts for all of them, all of the radio galaxies in our sample. So the absence of optical counterparts and hence that of redshift is a huge constraint when it comes to calculating luminosities and hence deriving luminosity functions. So we need a way to assign redshifts to the radio galaxies in our sample that do not have an optical counterpart. So we again go with the same data that I used for my previous study, but not with the mid-infrared magnitudes. So I'm not explaining this here. We have optical photometry, spectroscopy for some, and radio flux density values. Sorry. Okay, so I divide my sample into three. GEM corresponds to, it's a short form for galaxy and emu, sorry, gamma and emu. So GEM1 corresponds to the sample that has optical counterpart. So basically a spectroscopic redshift and the radio sample. GEM2 corresponds to the radio galaxy sample with photometry, but not spectroscopy. So there is no redshift for GEM2, but we have an additional photometric values coming from the gamma. GEM3 is the sample without any optical counterpart. So if you look at the numbers, it's like 72% of the radio galaxies do not have an optical counterpart. They are basically alone. They might be okay with it, but I'm not. I need redshifts. So the key idea in this work for luminosity functions is that I'm going with the assumption that radio galaxies within the same radio flux values, they share their astrophysical properties. If you take my entire sample of radio galaxies and divide them into bins of radio flux densities, I take one bin, then I say that all of those radio galaxies, they have the same properties. For instance, redshifts. They might be having the same redshift. It's not a very good assumption, but this is what we have, at least. This is what I have, at least for now. Go with. Okay, that's the assumption. So I'll explain the procedure of redshift estimation for GEM2 sources. Just to remind, GEM2 sources have photometric and optical counterpart with photometry, but not spectroscopy. Okay, so I'll double straight in. So we have, let's say that I have the GEM1 sample here and GEM2 sample here. I bin both of them into equal bins of radio flux densities and optical R band magnitudes, because we have both this data and R band magnitude acts as an additional constraint. And in the GEM1 samples bins, if I look at it, I'll have a redshift distribution because they have the spectroscopic counterparts, they have redshifts. So I take that redshift distribution and I look at the same bin for GEM2, and let's say that bin has 100 galaxies, 100 radio galaxies. I assume that this distribution is normal, and I take 100 random numbers, 100 numbers randomly from that distribution, and those 100 numbers are assigned as the redshifts for the radio galaxies in this bin. So at the end of that procedure, I have in that one bin, I have redshifts, predicted redshifts for the radio galaxies. This procedure is repeated for all of the bins, and in the end, I'll have a predicted redshift value for all of the radio galaxies in the GEM2 sample. It's a statistical approach. And this is how the distribution looks like. And the orange histogram here corresponds to the predicted redshift values by the procedure that I just explained. The same procedure is repeated for GEM3. Heads up, we don't have the additional constraint of R band magnitudes here. Okay, the same procedure and the predicted redshift distribution for the GEM3 sample is shown as the orange histogram. So if you look at it, it's a large sample, the GEM3, and its redshift distribution closely follows the reference sample of gamma. So this is not that good because there is no way that all of these radio galaxies lie within a redshift value of 0.4 as per gamma's maximum value. So this will have some implications when we go on to deriving the luminosity functions. I'll talk about that later. As I said, I need to look at the luminosity functions separately for star forming and AGN population. And for the classification, I go with the BPT diagram here because the study, the Moch and Sadler results that I mentioned earlier, they do their classification using the BPT diagram. And they include their composite galaxies The orange ones here, among star formers. So I follow them blindly to do all these procedures. But again, to do the classification, I can only do that for the GEM1 sample, those with spectroscopic data. So again, with some statistical magic, I assign classifications for the GEM2 and GEM3 samples. And in the end, I have a predicted redshift value and Bayesian classifications for all of my radio galaxy sample. And I derive the luminosity functions, and this is how it looks like. It is largely overestimated. The blue data points here are the radio galaxy, the sample that I was talking about. The red and green ones, that's a subsample with optical counterpart. So GEM1 and GEM2. The colored lines, green and red, those are the analytical fits to the luminosity functions done by Mochi and Sadler. So that's just to compare my luminosity function results. And these lines are allowed to evolve according to the redshift as we go to high redshift bits. So on that note, I have the luminosity functions in different redshift bins here. So here it's 0 to 0.5, the high redshift 0.1, 0.2, all up to 0.7 to 0.8. So it is clear as daylight here that these blue data points are highly overestimated. That is not good. But if you look at it, those radio galaxies with an optical counterpart, red and green data points here, they kind of follow these analytical fits. So that's something to hope for. And relying completely on that, all the luminosity functions up to this bin, 0.5, I keep the luminosity functions for the subsample as it is and take all these blue data points here until 0.5. I'll do something, I'll reassign their redshifts and then reassign their redshifts to a value above 0.5. This most probably happened because of the distribution that I talked earlier, because for the GEM3, those radio galaxies without an optical counterpart, it was closely following the reference sample. That's probably the reason why the overestimation happened in the low redshift universe up until 0.5. So to mitigate that, instead of following the gamma redshift distribution, I look for a much more realistic redshift distribution to higher redshifts. So this study was done by Vanessa Smolchich in 2017. So they have a much more astrophysically valid redshift distribution for AGN up until 5.9. Long story short, I do all the procedure that I did earlier by assuming this as the standard distribution and then calculate the luminosity functions again. And all of those blue data points disappeared. And you can see that if you look how the red and green data points behave. Well, by the way, I didn't mention this. The green data points are the star formers and the red data points are the AGN. And the corresponding colored lines are the analytical fits for those classes. If you forget about the colors for a while and look at how the data points behave, here it's looking fine. It follows the lines fairly well. In all of the panels, the behavior is almost fine, but the AGN are not doing what I expected it to do because AGNs are severely underestimated in all of these high redshift bins, also up here. That means we have to do something else. So this is where the point that I mentioned in the previous talk, the fact that not every AGN will show up everywhere. And the fact that we used only an optical diagnostic to select AGN for this purpose probably is the reason why this discrepancy happened. So to take radio AGN into consideration, every galaxy in this sample with their radioluminosity about 10 to the 23.5 watts per hertz, their classification is now redefined to be an AGN. That's almost fair because this luminosity corresponds to a very high star formation rate, around 100 solar masses per year. And it seems like that is a fair choice for a luminosity threshold to define a radio AGN. We do that procedure, and this is how the luminosity functions look like. This is pretty remarkable according to my supervisor. All the data points follow what they should follow. The red data points are the AGN. They follow these dashed red lines in all of the panels. I haven't quantified this like in a statistical fashion. I'm just doing an eye-based comparison. And this is a preliminary work. So I have a lot of work to do. But for the time being, it seems like that it is doing a good job. And that's good. I had a redshift distribution here to look at. So what if in one case I don't have anything as a reference? In that case, I'm again going with a very simple thing possible. I assume that all the galaxies in the universe are uniformly distributed up until a redshift of 5. Everything is everywhere. Same procedure, I sample the redshifts from this distribution and do everything again, and then this is how the luminosity functions look like. Again, this is also pretty remarkable, maybe. There are data points, but the point is that star-forming galaxies and AGN closely follow all the reference line that we want. It's all looking pretty good, except in the high redshift planes. It gets a bit wonky here because it's a bit underestimated, but as a whole, in general, with the simplest of statistical tools, we are able to derive radioluminosity functions and show that it is doing a pretty good job. And there is a population of star-forming galaxies here in the faint end in the low redshift panel that I conveniently left out previously. These are most probably low radioluminosity dwarf radio galaxies. They usually show up in optical luminosity functions, but rarely so in case of radio. So in that sense as well, it is, I think, pretty good to see these population here. That was the part 2. Thank you for listening. Well, just to conclude, the main point here is that simple alternatives like using simple statistical approaches and redshift distributions, for instance, the uniform distribution that I showed, these techniques act as an alternative in the absence of optical counterparts to radio galaxies in the era of current and new generation radio surveys like ASCAP and SK. I was asked to say this, that's why. Anyway, thank you. Thanks for listening. Yes.
So I don't know too much about AGN, so
fine.
Forgive me if this is a naive question. But do you know what the physical processes could be that would cause only emission in radio and not other wavelengths?
That's a good question. I think from what I've read, what I found is that it's more like a mechanical process. So when the jets are produced, to interact with the medium, and that results in the emission of only in the radio part of the spectrum. So what happens in AGN is that in accretion, emission coming from this process mostly peaks in the ultraviolet and visible. That gets inverse Comptonized to go to soft X-ray, and then dust picks up the radiation, and that goes into infrared. That's how the entire spectrum gets populated. But in the case of lurks, this doesn't happen. It's mostly mechanical. That's what information I have. If you need more, I think I'll need to talk about it later.
Okay.
Yes.
Great talk. I found it really interesting how you estimated the redshift distributions for things that you didn't have the redshifts for. And I was hoping to hear a little bit more about how your statistical approach is sort of motivated. Like, how do you know it is going to do a good job of reproducing?
I didn't.
Huh?
I didn't know. I just did it. You're talking about the redshift distribution, right?
Yes.
Yeah. So for me, the point is that I didn't have any optical counterpart for my radio galaxies. And most of the time, what people go for is a machine learning approach, which kind of put things in a black box. We don't know what's happening. We get some results, and things sometimes seem to do a good job. I actually used the easiest way possible. So you actually want to know how I did or what I did?
Yeah, I couldn't quite follow the steps that
okay.
you
So
were
if
saying
I am,
for estimating.
if I want to re-explain the GEM2 thing, so it's a sample of radio galaxies with optical counterpart.
Right.
Okay. So, but without spectroscopy.
Yep.
So I have the photometry, optical magnitude.
And then do you have photometric redshifts or not?
No, I didn't use the. I didn't look for it.
Okay.
I just said I need spectroscopic values. That's it.
Okay.
So what I did is I have the 2 samples, GEM1 with spectroscopic data, redshift, GEM2 without. But this has an additional constraint of R-band magnitudes, optical magnitudes. The point is that if you have an optical source associated with it, it actually additionally constrains at what distance, let's say, the radio galaxy can exist.
Because you know, like the redshift dimming and reddening of the object.
Sorry?
You know, like how much
No.
the color would be redshift.
But since this is detected in gamma, gamma has a redshift limit up until 0.4 0.4 for my sample. So it wouldn't be beyond that at max. But since they don't have spectroscopic redshift, these radio galaxies can still live at high redshift. That you can see that here in this predicted distribution. It goes up until 0.8.
Right.
So that was the procedure then is that bin them according to optical magnitudes and radio flux densities. Take the distribution from the GEM1, which has the redshift values. So in that bin, I have a redshift distribution.
And then randomly assign.
Assume that to be normal, and then randomly assign.
Okay.
I can assume this distribution has to be anything. Well, I have to fit it and then see whether it's a good fit to be a Gaussian or not, and then sample values from that distribution.
And would you have expected Gem 1 and Gem 2 to have similar redshift distributions, or is Gem 2 like a sample in this case that is going even deeper?
Yeah, that was a surprise. Yes, since both of them have gamma counterparts, I expected them to be almost for the same thing. Yeah. But as I said, there is a set of radio galaxies without spectroscopic redshifts, but still observed by the gamma. So they can still be outside the limit of what gamma can probe. That's what's in here. But what surprised a lot, well, not surprised, what kind of expected was the behavior of Gem 3. They're not at all expected to be in this limit. Because not this many radio galaxies can lie in the redshift universe, but still they follow the same thing.
Thanks.
Sarah has a question online.
Yeah, I was just wondering whether, sorry, it was based on your final slide and kind of talking about that estimating radio properties in the absence of optical data, but in the next year or two, Australia will have access to optical imaging across 6 bands from LSST. So I'm curious how that would factor into these kind of analyses going forwards.
Okay, I'm not sure LSST comes with photometric data. If that is the case.
Yeah, so it's LSST is optical photometry across 6 bands. So it would give photometric redshifts out to a redshift of 1.4.
Okay, so in this work, I've only used one band, R band, as a single constraint. But if you have more information from more bands coming in, that can be used as an additional constraint, at least for those radio galaxies with optical counterpart and without spectroscopic data. If that is the case, I think it can be used to improve the results or constrain the redshifts in a much more robust fashion. But I think that will be a good extension of this work because we only looked at gamma, and if the LSST is providing much more nicer photometric values, that might add large value to the new set of radio galaxy samples coming in.
Yes, yeah, I would agree.
Does gamma not have, do you not have other bands available?
I did, we did, but I didn't use it because I was submitting my thesis and
no, understand.
Yep.
Use Gem 1 here to predict how Gem 2 and 3 would behave. Did you use Gem 1 to predict Gem 1 to see if it...
Yes, that's a very good question. That's one of the suggestions that I got from one of my co-supervisors. No, one of my examiners. But that is actually a very good suggestion, yes. And it will be a test to see how good is the technique that you're following. Yes, I haven't done it, but it'll be good to see.
Any other questions?
Just a really quick one. You know, when you right at the start in project 1 were defining your AGN fraction, and you are like the ratio of these things is greater than 3.
Yes.
Where did that number 3 come from?
Ooh, again. That was a choice. Again, it's a bit conservative. It's like the main point here was for me to have an AGN selection criterion. So I have to say that put some value there and say anything above this might be an AGN. But 3 is a bit conservative because since we are relying largely on radio excess, in most cases, it might be that any galaxy with any value above the predicted radio flux, it might be radio AGN. The point here is that we want to make our AGN sample here really reliable than complete. Because the point here is that we are trying to compare our AGN samples with other techniques, agents from other techniques, and we don't want any contamination. We need a pure set of radio AGN, and to see this is how it looks like. If I'm going to do an additional study based on this project, maybe we can reduce the threshold value to 2 or 1 or any other number that people like, and then do the same thing. So it was just to demonstrate that this thing works, and I'm choosing that as a radio AGN sample and saying this is how it looks like.
So it's an arbitrary number significantly greater than 1, but not too much greater than 1.
Yes, something like that.
Great. I love it. Big fan of picking arbitrary limits. It's fantastic.
I had 2 questions.
Sure.
So you included composite galaxies in your AGN. Do you know, and you broke down the fraction of AGN contribution to, is that what it was?
Sorry?
I guess how much of the composites contributed to your AGN sample? Like what's the fraction of composite galaxies in your AGN?
No, I didn't look at that number.
Oh, okay, right.
Because, well, that might help, but at least for the purposes of this work,
Right.
that didn't come up as a thing. But that's
Okay.
actually a nice way because we included composites among agent because even for some composites, there might be a large contribution in their entire emission coming from agent.
Right.
So we want that again to be complete.
Right.
Those were.
And my second question was, at the very end, you had a population of low radioluminosity, low excitation radio galaxies.
Yes.
What's driving the radioluminosity in those? Do you have any idea? Or no? Okay.
Well, it's again, since they are radio AGN. So
Yeah.
Again,
So they definitely have an AGN according to the radio classification.
Yes.
Right.
But it's not driven by accretion. It's driven by the mechanical processes, which is kind of one way proposed is that the hot gas in the intergalactic medium that gets attracted or fall into the gravitational potential of the black hole, and then in that procedure of falling, it mechanically gives out some energy. And if you look at the power of these processes, it seems like the power that you get from the AGN, the power which is expected from this process, it matches.
Okay.
It is proposed as one of the possible mechanisms to explain the low process.
Right. Okay. And then those, so low excitation radio galaxies, that doesn't LERGs, they don't scale with stellar mass, right? Are they low stellar mass or are they high stellar mass galaxies?
It depends.
Does it correlate at all?
From the papers that I've read, most of them were identified in high mass galaxies most of the time.
Okay.
But here we see it in case of.
Okay. I guess I was confused because I thought it could have been how do you have a low mass galaxy that's an AGN?
It's, that's the point. It's possible, right?
Okay, right. That's really cool then. Because I didn't think.
Like you said, most of the time AGN are associated with massive ellipticals.
Yeah, exactly. It's a defect.
That might not be the case always.
Yeah.
Every galaxy has a supermassive black hole.
Yeah.
That's what most of the papers in extragalactic astronomy starts with.
Yeah.
We all have black holes in centers of galaxies. If they are, it could be an AGN.
Yeah. No, that's super interesting. So that's really cool work. Cool. Is there any other questions? Awesome. I guess that's a wrap. Can we thank our speaker once more?
Thank you all for listening.
I need to tell you something.